All right, here we go. All right, so industrial communication. Actually, tonight it's going to be more about something called EtherCAT. It's pretty much going to be 90% of the presentation will be about EtherCAT. And then we'll touch a little bit on something called OPC-UA, which probably needs its own presentation. OPC-UA, and then there's a related technology standard called MT Connect that is quite popular in North America. Those two will do it a separate presentation. So let's get started with this one. Of course, my name is Adam Cook, if you don't know already, and I am a core contributor to a effort here in Detroit called Built in Detroit. It's really a workforce development effort focused on robotics, industrial automation, mechanical design, factory floor design. Really, we're trying to eventually make it into a very hands-on experience. And, we're hoping to somehow bring that experience worldwide through, internet technologies. And YouTube will be one place. We're building other platforms, and we're acquiring hardware here in Detroit that we're hoping to distribute, potentially in partnership with Chapter 153. We'll have to talk about that, but we're really hoping to turn this into not just a YouTube experience, but a real hands-on experience. I mean, that's how you really learn, is by putting your hands on actual industrial hardware. So, that's kind of the gist of Built in Detroit. And of course, we're doing this in collaboration with Chapter 153 tonight. And everybody tuning in should be from 153. And of course, we appreciate you being here. If you ask questions during the presentation, I probably won't see them until the end. But we'll circle back to the questions at the end and touch on those. Okay. Also, here in Detroit, we are sponsored by Bamboo Detroit, which is a co-working space. And actually, I gave this presentation already to Bamboo. And of course, we appreciate their sponsorship here in Detroit. Particularly, again, when we start doing hands-on activities, we'll need physical locations to do those things here, and maybe also in Chapter 153 in collaboration with Chapter 153. And September 12th, tentatively, we'll do the next presentation, Industrial Motion Control, which, again, if you attended the one before this one, it was CNC controls, which is the control part, like the controller part of the machine. Now we're going to be talking about essentially the nerve center of the machine, how each device in the machine communicates to one another, or at least a popular technology that the devices use to talk to each other. In industrial motion control, we'll start getting a level higher. All right, we'll actually talk about how the machine moves. A machine that doesn't move isn't useful. So motion in a machine is very, very important. And so we're going to go up a level higher. I'm not sure about this date yet, but I'm kind of putting it out there. It should be sometime in September. I will work with Ron Gill and get a firm date established for that. But look for this I really hope to make this one a kind of a nice one. I want to break apart some servo motors and some motors in 3D and talk about the parts and talk about how they work and to talk about how to size motors and all that other stuff. So I have to put that together, but that's where we're going next. This one might be cut off a little bit, again, in the lower right-hand corner, but today we're going to be talking about industrial communication. What this is going to be building for us in terms of future experiences is I really want, again, to get to a place where we're actually programming our own EtherCAT main and node stack. And we'll go through what that means. Implementing our own. You can purchase these things off a shelf today, and that's great. And you'll see that in factory floors. Okay, but to really learn how to do sort of industrial computing, industrial programming, it's always helpful to get down to the metal and program it yourself, even if it's just an educational experience. It'll allow you to learn better. I can talk about these slides all day, but until you're actually in the stuff doing it, that's where it really solidifies. We're also getting our hands on some EtherCAT motion and safety hardware trainers. They're about the size of a small suitcase, and inside there'll be an Ethernet compatible controller, terminal blocks, and servo motors, and some safety modules. And really, that too, when you have the hardware in front of you and when you're working with the hardware, that's when these topics really set in. That's when you really get the knowledge. And then lastly, the one you probably can't see is OPC-UA via Python programming, which basically we would use OPC-UA and the Python programming language to basically allow two industrial devices to communicate with each other, or an industrial device to talk to the cloud, which is a popular strategy nowadays. You have factory floor and you have devices and they're transmitting data and you want to push that data up to the cloud. You can use OPC-UA to do that. And I'll talk about that at the end of this presentation a little bit more, but that's really where we're going with this. Hands-on activities from this presentation tonight. Okay, so let's get into the presentation itself. This is a video. Watch carefully how everything is working, how all the axes are moving. This is a machine. This is a CNC machine machining parts. Watch how everything's working. Okay, so what should have jumped out at you from that video, and I showed that video during the CNC systems internal presentation I did a couple months ago. I showed the same video. And the reason I'm showing it is because you can watch all the axes move and you can see the machine tool cutting the material. Everything is highly coordinated. Everything has to move in a certain ballet. in order to produce the part that you want. And so there has to be a communication strategy, which is what we're going to talk about, a communication strategy internally to the machine to allow that to happen. All these devices, all these servo motors, all these axes to talk to each other. Otherwise, there's no coordination. You're not going to get that kind of coordination to make useful parts. Let me show you another video. This one has some German in it. I can't speak German, but this is a flexible machine center. I showed this one last time too. It's got a kind of a vertical gantry in the back. There's shelving for cooling and fixtures. You have two operator cells here on the left, and then two machines that can be swapped in and out on the right. It's called a flexible machine center because you can mix and match, change the configuration, you know, fairly freely. There's like a pendant to schedule jobs. And so you can see this vertical gantry is taking tooling out of the pallet and it's putting into the machine. And the machine is going to machine a part on it. And here it represents it's working at night. You can shut the lights off in the factory, and it can work. It can work basically at night when everybody's gone. The point of that is, again, there you have a situation where devices are talking to one another. Whole machines are talking to each other. And it has to be highly coordinated. It has to be quantifiable how they talk to each other so that useful work is done. Okay, and there's special technologies to do that. So let's back up a bit. We're going to focus a lot on a CNC machine tool, like the first video you saw, and then the second video there were several in that flexible machining center. But you have a part, you've designed it in CAD, and now you want to machine that part. You want to create that part in a machine. Okay, so you model it up in CAD, right? You go from a CAD, you produce a 3D model. All right, you take it to a computer-aided manufacturing program. You create a CNC program, and then you feed that program into the CNC machine controller, and the CNC machine will hopefully create the part you want, the part you designed. It'll machine it out of a solid block or whatever. Now, the key here to understand is every single time, if you feed this program into your CNC control, every single day of the week, every single minute of a day, every time you feed that same program into your CNC machine tool, you should get the same part out every single time. That's called determinism, deterministic behavior. For a input, for a single input, you get the same output every single time. And so to do that, you need to have an internal communication structure in your machine such that every time something talks to the controller and the controller talks to all the devices, that it's deterministic, it's quantifiable. As a systems designer, as a machine designer, you want to embrace a technology that's quantifiable. Okay, let's proceed. Here too, the flexible. So this corresponds to the second video. All right, you have multiple machine tools, multiple CNC machines, and they're all hooked up together with something called an industrial Ethernet to a flexible manufacturing system. So all the coordination between these machines is quantifiable. I also showed this during the CNC, the last presentation I did on CNC internals. When we talk about a controller, when we talk about an industrial controller, the brains of the machine, okay, you can't just have Windows, Microsoft Windows, like everybody uses pretty much every day on their computer. Why? Because Microsoft Windows is designed for performance. It's designed to give consumers a good experience, a good computing experience. But it's not designed, vanilla Windows is not designed to give quantifiable, deterministic behavior that a machine tool demands. There could be tasks that need to get done on a priority. Someone could hit the emergency stop on the machine, and then there needs to be some tasks that get prioritized. There needs to be deadlines. If something doesn't happen, if a task doesn't happen in a certain amount of time, it's a system failure. There has to be a system to manage that. There has to be, quantifiable cycle times associated with that. Windows doesn't provide that out of the box because it's not an industrial operating system. However, what is a popular strategy is most computers these days have multiple cores. And in this case, in the upper left, you have 4-core computer. What if you took one of the cores and you made that a vanilla Windows 10 installation, but the other 3 cores you grabbed and you let those run what's called a hard real-time operating system that gives you those guarantees, that gives you that platform for quantifiability. So you have the benefit of the Windows. When you're looking at a machine tool, you may see a very familiar Windows interface. But underneath, what you can't see is that 3 cores of that are a hard real-time system that's giving you, the machine designer, the systems designer, a platform to build quantifiable applications on top of industrial applications. So that's what's happening inside of the brains of the machine, the controller of the machine. Okay, now let's put that in our pocket. Let's get into like communication part. I won't say in the beginning, but in the past, if you wanted to hook up, decades ago, if you wanted to hook up two devices, the option that you had was serial communication. And there were two standards that govern that, RS-232 and RS-485. RS-232, the problem with it is you could only hook up with this one cable. You could only hook up one device to another, and that was it. Very limiting. And the cable length was very short by necessity. So very, very limiting. Then they came out with RS-485, which I believe could connect 32 devices together. And the cable lengths could be longer. But it was still very limiting because, let me catch up here, because data was being transmitted serially through the cable. Okay, ones and zeros straight down the pipe. A very inefficient, very slow in terms of bandwidth. Bandwidth being, if you can imagine on a highway, the number of lanes is sort of similar. The amount of cars that can go past it, this serial communication had a very, very few lanes. So you couldn't push a lot of data through. So for very rudimentary machines, for very rudimentary tasks, this was fine. But today's machines are today's machines and robots are very, very complicated. And we'll see that in the subsequent slides, how complicated they can get. But, in the past, that was okay. Decades ago, that was okay. Today, it won't work anymore. So we needed something else. Okay, so what is fieldbus? Really, all it is a digital communication system used in industrial automation and control systems. All right, and again, a key feature of fieldbus is real-time communication between industrial devices. That's the whole point. Quantifiable communication. If you don't understand what your machine is doing and every single key element of the machine, how the controller's designed, how each device talks to each other, the performance of each device, then you don't have a machine you understand. And if you don't have a machine that you don't understand, you can't put it out in the field. It won't do useful work. It'll make bad parts. It'll hurt somebody potentially. You can't have it. Just can't have it. Okay, so what ended up happening was there were a lot of attempts at different fieldbus communication technologies. But something came along called Ethernet. And we should all be very familiar with Ethernet because it's really something we all use every single day. It's really a family of wired technology standards, devices, that are used as the backbone for the internet. If you take an Ethernet cord and you plug it in the back of your computer, you're using these technologies. We should all be familiar with that. And the internet was built atop Ethernet, essentially. And so you really had an ecosystem of cables, of devices, of strategies, of technologies that kind of emerged around Ethernet in order to build the internet, in order to enable the internet, essentially. And someone got it in their mind, a few people actually got it in their mind, well, why don't we piggyback? We need communication for industrial devices. Why don't we piggyback on top of Ethernet? Because somebody already did the hard work for the internet. Why don't we piggyback on top of Ethernet and try to build a real-time communication technology stack on top of Ethernet? Now you had to do that. You had to build that separate stack, a tailored stack for industrial systems, because the internet that we're all used to is really not designed for quantifiable communication. It has all kinds of different media types. It has quality of service. It has, it's for watching videos and text messages and non-industrial uses for banking and for everything else, and for non-industrial uses. And so that won't work for us for machines. We need something more robust. We need something more real time. These 4 organizations, there were more organizations and more technology standards. But these 4, I think, are probably the most popular, give or take. Of course, we'll be focusing solely on this presentation in EtherCAT, the upper left. But Ethernet IP is fairly popular. It's a different technology. It's a different standard in North America. And then in Europe, you have EtherCAT, PowerLink, and Profinet. Okay, and again, I won't talk about all these technologies. I am rather unfamiliar with PowerLink and Profinet myself, and I don't even know if I'd be comfortable talking about those technologies. But I would say that they're rare-ish. Probably, as time goes on, it seems that everybody's kind of going to EtherCAT because it has distinct advantages. And we'll talk about some of those in a minute. But here on this, you can kind of see it from a data perspective. Each of these technologies is supported by a different standards organization, a different technology group. And each one of these technology groups allows member companies and device manufacturers and servo drive, manufacturers and IO device manufacturers to partner with the technology group in order to standardize their products against, the standard. And from this chart here, you can see that, clearly EtherCAT has the most mind share, the most adoption in terms of third-party vendors that are standardizing their devices against the EtherCAT standard, making them compatible. And to a lesser degree, Ethernet IP, which stands for Industrial Protocol, PowerLink, and Profinet are other ones. And you can see those see much less adoption. So EtherCAT is really kind of emerging as the de facto fieldbus standard, which is why I'm talking about it in this presentation most of all. Okay, so let me catch up my notes here. So there is a reference model. You can think of it as sort of an abstraction layer that this model basically forms the basis for systems communication, for remote systems communication. So anytime 2 devices talk to each other, there can be this layer, this stack. And under this stack, there's various technologies. Okay, so on the left-hand side, there's this reference layer. On the right-hand side, there's what EtherCAT uses. Let me explain. So if you do any sort of online banking, okay, if you go on your web browser and you do some banking, Okay. All of these layers are being used. All of these layers have a distinct technology under them that are being used to secure your session with the bank servers, make sure nobody's snooping in on your connection. That would obviously be bad if you're in a banking relationship. There's technologies that handle the transport of data. There's technologies that handle how data is converted as it's being sent. Okay, it's a very complex ballet of systems that are happening. It seems simple to you on the web browser, but behind the scenes, there's actually a very complicated set of layers that are interacting with each other from top to bottom that are allowing you to conduct transactions with your bank securely. Okay. For EtherCAT, we don't need all that. We don't need all that. We don't need that kind of security, because when you're in a relationship, when you're in a digital relationship with your bank through their web portal, you're really going across, untrusted territory. Let's put it that way. But inside of a machine on a factory floor, we don't need all that complexity. We know what it is. There is no, bank relationship there. There's no need for super high security requirements. Just talking amongst the devices inside of the machine. So EtherCAT gets rid of all these unnecessary layers, from the application layer to the network layer, and then it produces it specifies its own technologies for the data link layer and the physical layer. Very important in systems design, very important in machine design, to get rid of unnecessary complexity. Unnecessary complexity slows you down. Unnecessary complexity can add unquantifiable behavior into your system. It can add expense into your system that you don't need. So EtherCAT boiled it down. I just need these two elements right here. Okay. What EtherCAT does, the relationship EtherCAT does, is it has a simplistic main controller, main device, and downstream nodes. And we'll see that graphically in a minute. So it's, the internet, if you looked at it graphically, is very complex. All these different device types and communication standards and all this stuff happening out there. But inside of a machine, we want to keep things simple. So we want to keep simple hierarchies. We want to keep simple device descriptions. Okay. So one thing I want to make clear is that some of the industry terminology, I think, is racially insensitive, in my view. So in documentation for EtherCAT, and you'll see some of it on this presentation, they will use a master and slave terminology to describe the device types. I will use main for master, and for slave, I'll use node or secondary. I do think it should be changed, but I won't use those terms. But again, if you go on the EtherCAT site, if you go and see technical documentation out there, you will see these terms. Again, I'm a big supporter of inclusivity in manufacturing, and I think terminology like this should be changed. I don't actually think it's necessary. I think main and secondary are apt descriptions for what's going on. So just sort of be aware of that. Okay, so we have a machine tool. This is the picture of the machine tool video, the first video we watched. This is the actual picture. The video was inside of this machine, but this is, if you stand back, this is the machine that we're talking about here. You can see that there's a pendant here. And beneath the pendant, there's a controller, a CNC controller. And then inside the machine, you have, servo motors. And that's sort of shown graphically here. I know the bottom right sort of cut off, but that's the spindle motor. That's what it says. So you have the HMI, which you saw on the previous screen. It's got buttons, it's got dials, it's got a graphical user interface, so a human could understand it and interact with the machine. You got a programmable logic controller probably in there for somewhere for discrete logic for all the devices in your machine. You got a motion controller, and you got an NC kernel. And again, I explain a lot of this stuff. This NC kernel takes in programs, takes in G-code programs, and converts it into essentially signals to the servo drives to produce the motion profiles that you desire to make a part. So all the axes have to move in a coordinated way again. And on the spindle motor, there's, a tool, a cutting tool, and all the axes have to move in a coordinated way to produce the part you want, to cut out the part you want from a solid block. All right, here's how it looks more realistically. If, again, you were to rip out all the important devices from that machine tool and lay them on a table, this is what you'd see. Over on the left here, you'd see some sort of, controller, motion controller. All right, you see some terminal blocks, a PLC and some terminal blocks. All right, you'd have servo drives. Maybe this one on the right here is like the spindle servo motor. And then these here are for the 4 other axes. And then you have a control pendant. Okay, all of these devices have to be connected somehow. And they're connected through EtherCAT technology. So basically, you can use the yellow lines here represent, again, if you've ever taken an Ethernet cord and plugged it into the back of your computer, it's the same cable. The same cable used that you held in your hand and plugged in the back of your computer is the same cable you'll be plugging in these industrial devices here. They piggyback off that cabling. They piggybacked off of it because they figured, the cable manufacturers got it so cheap for the internet, for internet use. Why can't we just piggyback off that same cabling? And so in an EtherCAT network, you have the concept of a main controller, which is like the brains, the CNC control of the machine. And you can only have one main controller in your EtherCAT network. And then you can configure the network with all these secondary devices. You could have a PLC controller here, line connected to another controller. You can go down here. These are servo drives down here. You can connect it to a star pattern over here in the lower right. Any way you want. And this network, the way that EtherCAT works is this network pretty much self-configures. Once you connect these devices together with standard Ethernet cable, these devices know about each other effectively. So it's a very, very nice technology for a machine. In the past, you'd have to do a lot of manual configuration to get all the devices to talk to each other. As long as the devices that you're connecting together are EtherCAT certified, it should pretty much self-configure. There are ways to configure it manually, but it should pretty much self-configure. Okay, let's get into something else. There's this one, and then there's an animation. I apologize for the lower right. It's cutting off a little bit I know it's cutting off a little bit, but what is traveling through this yellow line between all these devices? What's coming from the main controller to all these secondary devices? A data frame. A data frame. It's a digital envelope. It's a digital envelope. You can think of it that way. It's a digital envelope. Inside of that digital envelope is datagrams, sheets of paper. You can think of as single sheets of paper. So there's a single sheet for the blue, there's a single sheet for the red, and there's a single sheet for the green inside that envelope. And each sheet of paper corresponds to these devices, each device. Okay, so there's a certain sheet of paper for a certain device. Okay, let's look at an animation. So what's happening here? From the main controller, there's this envelope being passed down in a single lane through all the secondary devices. And you can see that as this train, this data frame, you can think of it as a train stopping off at each station. As it passes each station, the device has the opportunity to read and or write to this train until it turns all the way back over to the main controller. Just a single lane of traffic. Constant. It's, this animation slowed down. It's a lot faster in reality. Very fast communication through this single lane, devices communicating. Essentially you could think of as passengers getting on and off of the train as it comes past. You can see another data frame here going through the station, exchanging data and writing data to each device. Okay, very, very simple. Again, you're building a machine, you're building a system. You want it to be simple. And EtherCAT provides this very, very simple communication standard, to talk to all these devices. Just a single lane of traffic, just passing by each secondary controller, exchanging information and reading information. That's a sped up. It actually is a lot faster than, it's microseconds, if not nanoseconds of cycle time between a very fast, very efficient way of communicating from a main controller to secondary devices. Okay, another feature of EtherCAT is, as you saw that train coming from the main controller and visiting each secondary device, there is the concept of essentially a conductor. You could think of a conductor standing on each secondary device. When the data frame comes into the device, the conductor stamps a timestamp on the ticket. And when the data frame leaves the device, the conductor stamps a leaving timestamp. So an in and out timestamp on each device, and each time that train goes through. Why is that important? Because the main controller, once the train goes through all these devices and returns back to the main controller, the main controller can use that information, use that time information to make adjustments into subsequent communication with the devices, with the secondary devices. So if you think about servo motors, you think about a motor rotating and then manipulating a ball screw, turning it into linear motion inside of the machine. What's coming off of the motor, what's being directly measured on the motor is position of the shaft. If you're dealing with stuff like, and I talked about this again in the last presentation, but in a CNC machine, you're really dealing with acceleration and deacceleration profiles in order to produce a good part with a good finish. You don't want your machine tool to be jerky in making a part. You want very smooth actions. You want very highly coordinated actions, so it doesn't break the tool and so it doesn't mess up the part. The main controller understanding all of, how long each device is taking to process this information and what the status of that information is in each device. The main controller can take that information and make adjustments. In terms of acceleration and deacceleration control and velocity control. So it's a very, very powerful piece. It's called distributed clocks I believe in the documentation for EtherCAT, but it's a very, very powerful feature. This concept of time and timestamps as the data frames are going through each of these secondary devices. Okay. Again, questions at the end. I don't see them right now if there is any. But I will get them to the end. Let's move on to, so that's the basic, I think, core EtherCAT standard. Okay, let's get into, basically extensions of the standard, because EtherCAT is 2, I think, decades old at this point. And since that time, requirements have evolved. Okay. EtherCAT G, or gigabit, is an extension to essentially the original EtherCAT standard. Okay. Look at this. Okay, uses LiDAR. It's a Waymo self-driving car. I won't explain the internals of the self-driving car, but you can kind of get the sense that there's a lot of data that this system needs to ingest and process internally in order to make decisions. A lot of visual information. Okay, these are the kinds of machines that are emerging today. So what the original EtherCAT standard supported a bandwidth, essentially. You can think of it again as lanes in a highway of 100 megabits per second. Was sufficient for the machines at the time. And it's really, even today, very sufficient for a lot of sort of normal machines and robotics. But the applications, again, are getting more intense, are getting more demanding in terms of the amount of data that you need to transmit through, these devices. And so you need a bigger highway to do it. And that's where, you can see at the top here, you had 100 megabits per second, then you had 1 gigabits per second, and then 10 gigabits per second. And these fall under the lower two, the bottom two fall under the EtherCAT G extension to the standard, which again provides, I believe, for the Ethernet, for the regular Ethernet cable, the one at the top, I think it's a 4-pin configuration. For the EtherCAT G and G10, I believe it's the 8-pin configuration. So all 8 pins are being used. Okay. Consumer internet, the kind that I'm using today to stream, is like 600-ish megabits per second. So, pretty fast for the normal consumer use. So you can imagine what a gigabit, 1,000 megabits per second, and then, 10 times that on the bottom here for very, very large bandwidths. Okay, so before I get this animation going, what is shown here essentially is the combination of two different bandwidths. So on the right side here, you have 1 gigabit per second cabling, a 1 gigabit per second backbone, if you will. And then you have on the right side sort of a normal EtherCAT 100 megabit per second configuration. Ethernet, the Ethernet standard supports what's called an Ethernet branch controller right here. What's happening here is that you have this on the on the left side, you have this gigabit backbone where you really need that high data bandwidth for some reason. Maybe some very hungry sensors or something. But in other parts of the machine, you can do with a normal 100 megabit per second network. And the reason that you would want to do it that way is because typically the higher the bandwidth, the more expensive the devices are, the more expensive the cabling is. And, if you can get away with primarily using the standard 100 megabit per second bandwidth, then go ahead and do that. But if you need a backbone that's 100 gigabits per second, that's fine too. How do you get the two to talk to each other? We'll use this Ethernet controller here, this branch controller. And what it's going to do is it's going to convert 1 gigabit frames into 100 megabit frames back and forth, and it's going to go back to the main controller. So you need this controller here to convert frame sizes and then send it back to the main controller. Here's a couple of different strategies to kind of, I guess, put a finer point on it. This one here, this third one, this third network is basically what we just saw. You have an Ethernet main. You have a 1 gigabit backbone. And then internally, somewhere else in the machine, you have this 100 megabit network, all connected by this branch controller. Okay, here's like what we were looking, this first one here is like what we were looking at the very beginning of this presentation. Just everything's just 100 megabit per second. You can see the communication time here, 230, still very fast. Still very fast for a lot of machines, a lot of robots. But if you need something more, if you need something around this communication time, 5 times faster, then this might be the configuration you want to reach for. Here too, if you just had, you know, if you just had this entire network being 1 gigabit per second, it's not as efficient as this third network here. So this third network here gives you a lot of bang for your buck. It gives you a lot of bang for your buck. And so if you're going to reach for something, you would try to kind of design your machine around this type of configuration. Okay, and then the last extension, I swear we're almost done here, is the EtherCAT power with a P at the end of it is another extension. So the idea here is all devices require power, some sort of power to do useful work. Sensors require power, and servo motors require power, and everything. A lot of things in a machine. In the past, you would run your communication lines, the EtherCAT, yellow cabling, if you will, to each device, to each secondary device. And then you'd have to run a separate cable for power. And then someone came up with the idea, well, why is it possible in some machines, in some systems, to combine those two cables into one? And that's EtherCAT P. And there's a short animation here about communication and power to all these different devices on a factory floor. So you have standard power cables here, EtherCAT to dependent. But then here we start running EtherCAT P compatible cables to various field devices out on the factory floor. Here's something for a conveyor, maybe some sensors up there or something. And here's what a set of a saw looks like. Not sure exactly what. Run that motor, other sensors. So again, if you have a factory floor and it's quite big, sometimes it's advantageous to just do one cable run instead of two. It's cheaper, it's easier for maintenance. That's the whole thinking behind, it's nicer looking, if you will. It's going to cost you more probably to do this, but if there's other advantages to doing it, then that's available to be used as well. Okay, here's how it looks graphically. So basically, on the top left, you have a standard Ethernet cable, and then on the bottom you have a standard, in quotes, power cable. What if you combine the two into a single cable? And that's how the evolution kind of looked there, I think. And yeah, here's sort of another. You have the EtherCAT main controller here, standard Ethernet connection. You saw some of that in the animation to these terminals here, and then you can distribute power and communication to all these devices and some field devices like cameras or a barcode scanner or something. This makes a lot of sense, I think, if you have a ton of devices, a ton of free devices out on your factory floor, and you don't want to run a whole bunch of cabling all over the place. It starts making a lot of sense to do it this way, and this is available to be used. So this is kind of it for the EtherCAT portion. This is the big view. Again, I apologize for the lower right-hand part of the corner. On the yellow part here on the right, you have a lot of the stuff we talked about, all connected through EtherCAT, or, well, yeah, all connected through EtherCAT technologies. Various devices, cameras, measurement devices, just of one possible network of an infinite number that you could possibly have, connecting your machine together, connecting all the devices in your machine together, or connecting the factory floor together. Okay, and in this case, it's more like a factory floor, because on the gray side, on this left side here, the main controllers are talking to some back office, normal business servers and applications. People in the office can view a visualization of how the factory floor is working, receive alarms on a tablet down here, or communicate to the factory floor by a standard Wi-Fi, but very inherently secure, because these are generally separate ports and they can be managed separately on the main controller. So there's an air gap between the sort of unsafe, unstructured nature of the office internet, if you will, and the quantifiable real-time part inside of the machine or inside of the factory. So there's like this gray part and this yellow part where they meet. There's sort of a natural air gap between those, some isolation. Okay, and the last, I only have 3 slides left. The last one is OPC Unified Architecture. We're going to briefly touch on this. So let's go a little bit back in history. In a long time ago, when there was Windows 95, I believe, there was a need for Windows applications that may have been written in different programming languages to talk to each other. Like Microsoft Word talking to some other application written by a different company. Those two needed to communicate somehow. So Microsoft developed a component object model, a set of APIs essentially, so that both the Microsoft Word vendor and the other application vendor could use a common interface to talk to one another. Okay, then the internet came along. And then there was a need for applications to communicate through a network. Like one on the desktop and one on a server. And so there was a distributed component object model created. And then someone had the idea in the industrial setting. So these are sort of consumer business technologies, comm and decom. Someone had the idea, well, can we bring some of that technology over to the industrial floor? How can we get 2 industrial devices, not consumer and business applications, but industrial applications, industrial devices, to talk to one another? And they piggyback off of decom and created OPC Classic, which is kind of going out of style. The reason it's going out of style is because, as you can see from the icons on the left, the COM, decom, and OPC Classic were exclusively Windows technologies. And these days on a factory floor, you have cloud environments, you have Linux, you also have Windows, but you have Macintosh computers, you have all these different, you have embedded systems, controllers of all different kinds, and you needed something more flexible. So basically, they essentially started from scratch and came up with OPC-UA. And that's where the unified architecture sort of comes from. The basic problem is this. So we've been talking a lot about fieldbus. Inside the factory floor, inside of the machine, again, you want a very simplistic, highly structured, quantifiable, deterministic environment. Okay. But these pieces of machinery or these devices, there's a real need to extract data from them these days. You have a CNC machine working on the factory floor, and inside of it has the fieldbus, the EtherCAT technologies that we just discussed. But the machine is also producing data externally, or data that can be used externally. And is there a more flexible technology stack, flexible data model that you can use to take the data off of the machine and push it into the cloud? You don't need fieldbus for that. You don't really need that sort of deterministic real-time communication between the machine and the cloud. You just want to put the data into a database so that later on someone can come over and crunch the numbers about the efficiency of the machine or how the machine's performing or if the machine needs maintenance. But it doesn't need to be real time. It doesn't need to be quantifiable. And that's where OPC-UA comes in. It's basically another industrial standard technology that can be used to extract data from the machine, and in some cases actually talk to the machine and make it and issue it very somewhat basic commands. Start, stop, do some kind of activity. That's where OPC-UA comes in. Again, I think it requires I think OPC-UA, to really understand it, it's simplistic. I think once you get your hands into it on the programming side, when you have a device, either a real device or a simulated device, and you hook it up to the cloud, you can see exactly what you have to do to connect those two entities via OPC-UA. And that's something that we'll discuss in a separate presentation. But that's it. That's all I have for my part here. builtindetroit.today is our main webpage. It is undergoing a massive reconstruction right now, but I do post events to it, and so you can check those out. Let us see if there's any questions. I don't see any questions, but of course, if you're watching this sometime in the future, I do pay attention to the comments if I have made any mistakes. If you have any questions, let me see about the Discord if anybody's on there. If you have any, if you have any follow-up questions, certainly put it into the YouTube comments and I'll take a look and I will respond. But I appreciate you joining me tonight, and have a good evening or morning, depending on where you are. Thanks.